Okay, let us now turn to another important point. The important point is is about integrability of some classes of functions. So let me write here as a title of this new chapter, classes of integrable functions. So, and in particular, we will prove that two very important classes of functions are in fact integrable, and these two classes are the class of monotone. When I say class, I mean set, okay, nothing more. Monotone functions and continuous functions. So they are integrable, okay? But of course, this does not mean then that an integrable function is always either monotone or continuous or both. There are many other functions that are integrable. If you will study the integrability of the Riemann function, then you will perceive that the class of integrable function is really wide. And also very irregular function can be integrated. Not so irregular like Dirichlet, but very regular function can be integrated. But I will specialize to these two classes of functions, okay? In order to do that, we need some theoretical notion. So we start with this lemma. Let me call it lemma 1 for this lecture. So let AB be an interval, a finite interval, closed. And then you have two partitions, P and P prime, of this interval AB. Then there exists another partition, P second, which is a common refinement of both P and P prime. Okay? And the proof is immediate. The proof is simply that you just take P second to be the union of P and P prime. So P second contains P prime, and so it is a simultaneous refinement of both. So I stop here. So as a corollary, we have that P second gives better upper and lower sums. So if you take the lower sum of the function f related to the partition P, this will be not larger than the lower sum of f with respect to the partition P second. At the same time, SF P prime is not larger than SF P second, and the same for capital S, so the upper sums. Capital S F P prime is not smaller. Remember that the smaller an upper sum, the better. It's not smaller than S F P second, and the same for capital S F P second. Okay, good. So, and now the second lemma will be used. We have that f is integrable. So we have again f from a, b to r, bounded. Say that f is integrable on AB if and only if for every epsilon larger than 0, again epsilon emerges, strikes back, for every epsilon larger than 0 there exists two partitions P and P prime such that the difference between the upper sum of one partition and the lower sum of the other partition is less than epsilon. Okay? It is sufficient to prove it for the particular case in which P and P prime are the same, so or equivalently, if there exists a P second partition of AB such that the difference between the upper sum of f with respect to the partition P second minus the lower sum of f with respect to the same partition is less than epsilon. And again we go to the proof. So, first, let us assume f integrable on AB. So, let us prove it by starting that f is integrable on AB. Namely, we have that the infimum of the upper sums on the partition, which is the, remember this is the upper integral, is equal to the supremum of the lower sums, supremum over all the partitions. So this is the lower integral, and by definition, when these two quantities are equal, this is the integral of f. Okay? So now let epsilon, an arbitrary number, let epsilon be an arbitrary number larger than 0. So an arbitrary positive number. So by definition of supremum, we have that there exists a partition P prime such that the lower sum of fp prime is larger than the sup of all lower sums, which is the integral. If I take this integral back by epsilon over 2, again epsilon over 2 because at the end I will have epsilon, so now we know this sort of trick of this sort of elegant strategy of using epsilon over 2. So by definition of infimum, there exists a partition P such that the upper sum of f with respect to P is less than AB f of x dx plus epsilon over 2. So now subtracting the first inequality from the second, so these are the two inequalities I am considering. So I do the second one minus the first one. So, and this is important in order to have the same inequality here, okay? This is minus, sorry, this is minor, this is major, so I cannot sum up. But I reverse them, adding a minus sign here, and then I can sum. So I end up with upper sum Fp minus lower sum Fp prime. The two integrals cancel each other, so this is less than epsilon. So I prove that if f is integrable, then there exists two partitions such that this happens. So let me call it this relationship asterisk. And now, moreover, consider a common refinement p second of the two partition P and P prime. And now compute the difference between the upper sum of the function f with respect to the partition p second minus the lower sum of the function f related to the partition p second. And now, of course, since p second is a refinement, the upper sum is not larger than the upper sum with respect to p. And the lower sum is not smaller than the lower sum with respect to p prime, but there is a minus sign, so we can say that it is not larger of minus s f p prime, that is less than epsilon by asterisk. Okay? So notice that here, go back to the lemma, we proved all the first direction. We starting from the integrability of f, then first we proved here, and then we proved here. Now we have to go back. Okay, and this we called two asterisk, inequality two asterisk, and now we close the whole proof by saying the following. Now we start from two asterisks and prove the integrability of f. So we close everything. Okay. Why we close everything? Go back to the statement of the lemma. I repeat that. Starting from integrability, we proved asterisk. Then we proved two asterisk. Then we go back here, and so you see that the chain is closed. Okay, this is a typical strategy for this sort of thing. Okay, so we go to two asterisk, and we have that the upper sum S of f with the partition p second is less than the lower sum sf p second plus epsilon. This is what we did here. We just took this minus s and put it here. Okay, nothing really complicated. Then from this relationship, we know we had that of course the upper integral, which is the sup of the lower sum, cannot exceed, again if you want by permanence of sign, cannot exceed any upper sum of f. Then, as we wrote above, this is less than little s f p second plus epsilon. And this is less or equal because this is the sup, the lower integral plus epsilon, okay? And since this is true, now this is true for every epsilon. For every epsilon larger than 0, okay? But again, since this is true for every epsilon larger than 0, you have that this must be true also for epsilon equal to 0. Otherwise, again, by permanence of sign, you fall into a contradiction. So what we have from here is that the upper integral is less than the lower integral, and by definition this must be less than the upper integral. This is by definition, or if you prefer, by construction of lower and upper integrals. Then the previous chain of inequality can be correct only if these guys are equal signs, indeed. So then we have that the integral, the upper integral of f is equal to the lower integral of f, and this implies that f is integrable on AB. And so the lemma is finished. And now we will use this, because in order to prove that a function is integrable, we just will prove that there are an upper sum and a lower sum arbitrarily closed. This is the only thing that we have to do. This lemma seems to be complicated, notation is complicated, but it is just an exercise on the supremum and on the infimum. Okay, now we go to integrability of monotone functions, so the first class of integrable functions. So theorem. A function f from AB to R monotone then f is integrable. On A, B. Okay. And so we go immediately to the proof. Consider again the democratic partition where all intervals are equal. Hmm? A equal to x naught less than x1 equal to a plus b minus a, the size of the interval, divided by the number of interval n in which the partition is made. This is less than x2, which is again a plus 2 times b minus a over n, and so on and so on, and less many dots x n minus 1, which is a plus m minus 1 over n times b minus a, less than xn equal to b. What am I doing here? Very, very, very elementary. This is the real line. Here you have A, here you have B, and here you have your partition. The first point here is a plus the size b minus a divided by n, and so on and so on. And now this partition is P, and compute the difference between the upper sum SFP minus the lower sum FP, and this is of course the sum of j from 1 to n of mj delta xj minus sum j from 1 to n small mj delta xj. Collect everything in just one sum. This is sum for j from 1 to n of capital Mj minus small mj times delta xj. Now this delta xj is the same for all, so this is equal to b minus a divided by n. So the next passage is to gather out the factor b minus a divided by n, and here to write down sum for j going from 1 to n of capital Mj minus small mj. Okay, and now let us reason on this. This is the key of the proof. And up to now, we did not use the hypothesis of the monotonicity of f. Now we use it, and we have to suppose something. Let us suppose that f is monotonically increasing. So let us assume f monotonically increasing. And let us see what happens if f is monotonically increasing. So this is A, B, you have things like that, for instance, and consider the partition, oh, it's too thin, then I will have many. Okay, this is simple. Okay. So what happens here is that okay, this is here. It is not really monotonically increasing. Sorry, let me do like that. Okay. Consider the first interval. So this is x0 and this is x1. So here we have that this guy here, this height here is m0, little m0, it is the infimum, and this is capital M0, the maximum of the, m1 and m1. This is the notation we used. Okay, let us go to the second interval, and here the sup, or the maximum, is here, is m2, so is f of x2, capital M1 is f of x1, but the important thing is that this point here, which was the sup, or even the maximum in this interval, becomes the minimum for the following interval. This is the key of the proof, because this is also small m2, and again capital M2 is small m3, while capital M3 will be here, which will be small m4, which will be equal to f of x3. Okay, this is the key. The key is that by monotonicity, here we use the increasing monotonicity, we have that capital Mj is equal to small mj plus 1. If it is decreasing, it is the contrary. Capital Mj plus 1 is equal to small mj. Then the difference between the upper sum related to the partition P minus the lower sum related to the same partition P is equal to B minus A divided by N, and then we have sum for J from 1 to N, and here you have capital Mj, you can say small mj plus 1 minus mj. This of course is true for n minus 1 here, and then we have, because here we have j plus 1, so we cannot afford j equal to n. Because for the last term, for the nth term, that is only the maximum here surviving. So we can also add here plus b minus a divided by m capital M n. So now collect b minus a over n, and here what you have is m2 minus m1 plus m3 minus m2 plus m4 minus m3 plus many dots, and then at the end you have plus mn minus mn minus 1 and here, sorry, it was not just, it was capital M n minus m, yeah. And here you have plus plus capital NM minus MN. Okay? Okay, if this writing is misleading, and it was a bit for me, so develop immediately in this form. It is much simpler, and it is clear that this is a telescopic sum, and everything cancels, sorry, not this, everything cancels out except the maximum and the minimum of the function. And now we will clarify what it is. We have b minus a over n. But now, what is capital Mn? This is the maximum of the function in the interval, and since the function is monotonically increasing, this is f of b. Analogously, small m1 is the minimum of the function in ab, so this is minus f of a. Okay. And now let us take n larger than b minus a times f of b minus f of a divided by epsilon. You know how it is, for instance, to recall us what we said at the very beginning. So, for instance, n equal to the integer part of b minus a, f of b minus f of a divided by epsilon plus 1. Then what we have is capital S fp minus small s fp less than epsilon. So by the lemma, by the previous lemma, we know that f is integrable in AB. This is a very important result, and let me complete it with the following remark. As I told you, but without proof, as I told you when studying monotone functions on closed interval, so a monotone function can afford how many discontinuities? Infinitely many. Sorry, discontinuities. Discontinuities. Of jump type. So what we proved is that it is possible to have an integrable function with infinitely many discontinuities. So quite tough functions can be integrated. So it is not true that in order to be integrable, a function must possess just a finite, must possess at most a finite number of discontinuity. Okay, this remark is just psychological, okay, psychological. Okay, discontinuities. Okay, this is the end. The lecture was longer than I expected, so I stop here this video and I go to the last one for this lecture about integrability of continuous functions.